Introduction to DNSSEC Validation. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will walk through DNSSEC signature validation step by step, using a real example of resolving www.example.com. Each slide will show one part of the validation sequence, with the actual DNS queries and responses you would see. Before we begin the validation process, let me explain the key concepts. DNSSEC adds cryptographic signatures to DNS records. When you query for a DNS record, you also receive an RRSIG record containing a digital signature. To verify this signature, you need the public key, which is stored in a DNS key record. But here is the challenge. A zone can have multiple keys at any time. There might be old and new keys during rotation, plus every zone has at least two keys. A zone signing key or ZSK with flag 256 that signs the actual DNS records, and a key signing key or KSK with flag 257 that signs the DNS key records themselves. To identify which key created a signature, DNSSEC uses key tags. A key tag is a 16-bit number between 0 and 65535, computed by running a checksum algorithm over the DNS key data. Think of it like an employee badge number. Instead of describing someone by their full name and department, you just say employee 31406. The signature includes this key tag so the resolver can quickly find the matching key. The validation forms a chain of trust. You verify the record's signature using the ZSK. Verify the ZSK using the KSK. Then verify the KSK is legitimate by checking a DS record in the parent zone. This continues up to the root zone, where you compare against a pre-installed trust anchor. Let us now step through each stage of validating www.example.com. Step 2. Fetch DNS key records. The resolver now needs the public key to verify the RRSIG signature. It queries example.com for its DNS key records. Looking at the dig command, we query for DNS key records at example.com with the plus DNSSEC option. The server responds with two DNS key records and their corresponding RRSIG. The first DNS key has flag value 256. In DNSSEC, flag 256 identifies a zone signing key or ZSK. The ZSK is used to sign all the regular DNS records in the zone, such as A records, MX records, and Quada records. The protocol field is always 3 for DNSSEC. The algorithm 13 matches what we saw in the RRSIG, confirming this is an ECDSAP-256 key. The long string of characters is the base 64 encoded public key material. When the resolver computes the key tag for this DNS key by running the checksum algorithm over its data, it gets 370. This matches the key tag in the RRSIG we received for the A record. So this is the key the resolver needs for verification. The second DNS key has flag value 257. Flag 257 identifies a key signing key or KSK. The KSK has a special purpose. It only signs the DNS key record set itself. Notice this key also uses algorithm 13. When the resolver computes its key tag, it gets 31406. The DNS key record set also comes with its own RRSIG. Notice this RRSIG has key tag 31406, which means it was signed by the KSK, not the ZSK. This is the expected pattern. The KSK signs the DNS key records, while the ZSK signs everything else. At this point, the resolver has the A record, its RRSIG with key tag 370, and the DNS key with key tag 370. It can now perform the cryptographic verification of the A record signature. Step 4. Verify DNS key RRSIG. The resolver has verified the A record signature, but it used DNS key 370 for that verification. How does the resolver know that DNS key is legitimate? An attacker could have injected a fake DNS key along with a matching fake RRSIG. To verify the DNS key records are authentic, the resolver must verify the RRSIG covering the DNS key record set. This RRSIG was signed by the KSK with key tag 31406. The verification process is identical to what we just did for the A record. First, reconstruct the signed data by concatenating the RRSIG metadata fields followed by all DNS key records in canonical wire format. The type covered is now DNS key instead of A, and the record data includes both the ZSK and KSK records. Second, compute the SHA-256 hash of this data block. Third, perform ECDSA signature verification using the hash, the signature from the DNS key RRSIG, and the public key from the KSK with key tag 31406. Fourth, verify the signature has not expired. If this verification succeeds, the resolver has confirmed that the DNS key record set, including the ZSK we used earlier, was signed by the KSK. The DNS key records are now authenticated. But we still have a problem. We verified the DNS key records using the key signing key, but the key signing key was part of those same DNS key records. This is circular. We verified the zone signing key using the key signing key, but how do we know the key signing key itself is legitimate? This is where the parent zone comes in. The resolver must now query the parent zone.com for a DS record that vouches for example.com's KSK. The DS record provides the external validation needed to break the circular dependency. Step 6. Verify KSK against DS record. The resolver now verifies that the KSK it received from example.com matches the DS record published in the .com zone. This is the critical step that validates the KSK is legitimate. The verification process works as follows. The resolver takes the KSK DNS key record with key tag 31406 that it received from example.com. It constructs the data to be hashed by concatenating the owner name in DNS wire format, which is example.com encoded as linked prefixed labels, followed by the DNS key RDATA, which includes the flags, protocol, algorithm, and public key bytes. The resolver then computes the SHA-256 hash of this data, since the DS record specified digest type 2. This produces a 32-byte hash value. The resolver compares this computed hash against the digest value in the DS record. Looking at the comparison, the hash bytes from our computation must exactly match the digest bytes from the DS record. If they match, the KSK is authentic. Why does this work? The DS record was published in the .com zone by the example.com domain owner when they set up DNSSEC. It is signed by .com's keys, creating a chain of trust. If an attacker tried to inject a fake KSK for example.com, the hash of that fake KSK would not match the DS record in the .com zone. The attacker cannot modify the DS record because it is protected by .com's signatures. At this point, the resolver has verified the chain from a record to ZSK to KSK to DS record. But the DS record itself came from the .com zone. To trust it, the resolver must verify the DS record's RRSIG using .com's keys, and then verify .com's keys using DS records from the root zone. Step 8. Validate root zone. The resolver has worked its way up from for example.com to the root zone. Now it must validate the root zone's DNS key records. But there is no parent zone above the root. This is where the trust anchor comes in. The resolver queries the root zone for its DNS key records. The root zone returns its ZSK and KSK, along with the RRSIG covering the DNS key set. The root's KSK has key tag 20326 and uses algorithm 8, which is RSA with SHA-256. The root zone is gradually migrating to newer algorithms, but as of now the KSK still uses RSA. The resolver verifies the DNS key RRSIG using the root KSK with key tag 20326. But how does the resolver know this KSK is legitimate? There is no DS record from a parent zone to check against. The answer is the trust anchor. Every validating resolver comes pre-configured with the root zone's KSK public key. This trust anchor is distributed as part of the resolver software, through operating system updates, or via RFC 5011 automated trust anchor updates. The trust anchor ultimately derives its authority from the ICANN root signing ceremony, a highly secure and publicly audited process that occurs several times per year. The resolver compares the root KSK it received against its configured trust anchor. If the public key material matches exactly, the root KSK is trusted. Since the root KSK signed the root DNS keyset, and the root DNS keyset includes the root ZSK, and the root ZSK signed the DS record for .com, the entire chain of trust is now validated. Looking at the trust anchor format, it is typically configured as a DS-style record or a DNS key record with the root zone's KSK public key. The resolver stores this and uses it as the ultimate source of trust for all DNSSEC validation. Validation complete. The resolver has successfully validated the entire chain of trust from www.example.com up to the root zone trust anchor. Let us review what was verified. Starting from the bottom, the A record for www.example.com with IP address 93.184.216.34 was verified using RRSIG key tag 370. The DNS key with key tag 370, which is example.com's ZSK, was verified as part of the DNS keyset signed by KSK key tag 31406. The KSK key tag 31406 was verified against the DS record in the .com zone. The DS record in .com was verified using .com's ZSK key tag 4459. .com's DNS keyset was verified using .com's KSK key tag 30909. .com's KSK was verified against the DS record in the root zone. The root zone's DNS keyset was verified using the root KSK key tag 20326. Finally, the root KSK was verified against the pre-configured trust anchor. With every link in the chain verified, the resolver now returns the A record response to the application with the AD flag set. AD stands for Authenticated Data, and it indicates that the resolver performed full DNSSEC validation and all checks passed. The application can trust that 93.184.216.34 is the authentic IP address for www.example.com. If any verification had failed at any point in this chain, the resolver would not set the AD flag. If the failure was critical, such as an invalid signature or missing DNS key, the resolver would return serve fail instead of returning potentially forged data. This protects users from attackers who might try to redirect them to malicious servers. The entire validation process happens automatically whenever you use a DNSSEC validating resolver. You can verify DNSSEC is working by checking for the AD flag in DNS responses or by using tools like Delve that show the validation status explicitly. Thank you for your attendance. Please consider subscribing to the channel and liking this video.